Welcome to CIS 116 IPv6 Fundamentals. This is a little introduction to IPv6. Okay, so first of all, guess what? IPv6 is here. I get questions all the time. When are we going to go to IPv6? Well, believe it or not, it's already here. So let's talk a little bit about the need for IPv6. The number one overwhelming reason is we're running out of IPv4 address space. So IANA, which is the prime delegator of IPv4 and IPv6 addresses, they delegate or allocate addresses to the 5 RIRs, Regional Internet Registries. They actually ran out back in 2011 of IPv4 addresses. The regional internet registries, all but 4 out of 5 have run out, and Afrinic, the last one that has some IPv4 addresses, is the last one, and they're due to run out either later 2019 or sometime in 2020. And this is where internet service providers and companies that want their own provider independent IPv address space. So, you know, companies, even schools can go directly to a regional internet registry to get their IP addresses. But as you can see that because so many of the RIRs have run out, the ISPs are the last ones with the IPv4 addresses, and they're beginning to run out. So ARIN, which is the Regional Internet Registry for, let's see, I'll use this right here, for North America, that's ARIN right there. They state that IPv4 depletion is the reason to make sure that you have planned to deploy IPv6. IPv6 implementation, IPv6 is the only viable solution to the dwindling pool of available IPv4 address space. Okay, so let's take a look at this. We're running out of IPv4. How big a deal is that? Okay, well, we'll see that the regions with the largest populations in the world have the lowest percentages of people connected to the internet. So you take North America, we're about 366 million people. Okay, compare that to Africa and Asia. That combined, we're talking over 5 billion people. You look at the internet penetration rate, we're doing pretty good in America. And we'll talk more about that towards the end of this presentation, because the internet is very, traditionally was very US centric. That's because we developed the ARPANET. But you compare that to Africa and Asia that have, you could just estimate between the two, maybe, 43, 44%, 45%. Of their population is on the internet. What would we say, internet penetration rate? But basically, half their population half of 5 billion people still need connectivity. We're just not going to get there with IPv4. And part of that reason is there's only 4.3 billion addresses. And we're running out. Yeah. All right. So I talk about, IPv6 being a sneaker wave. Sneaker wave, for those of you that are familiar a little with surfing or grew up in this area, know that it's, usually happens with a south swell, that the ocean looks really calm. And then all of a sudden a big wave hits, comes out of nowhere. They're very infrequent, but when they come big. So I think of IPv6 as kind of a series of sneaker waves. ISPs are running out or have run out of IPv4 addresses in some cases. A lot of major carrier transit traffic, I'll talk about what that is, is being carried over IPv6. So what we mean by transit traffic. So if we have ISP-A here that needs to send traffic to ISP, or let's go, to ISP-A, they're not directly connected to each other. They'll go through one or more other ISPs, and these are known as transit ASPs. So ISP-B sends the traffic to this transit ASP that then, so they receive it here, and then they got to carry it through their own network of routers until it gets to a router that interconnects to ISP-A. So we call this a transit AS. So in this case here, you know, when an ISP has to run both IPv4 and IPv6 on these connections, it's double the work. What I mean double the work, double the configurations, double the whenever you make a change, you got to make a change to both IPv4 and IPv6. More of an issue with troubleshooting because it's an IPv4 issue, an IPv6 issue, or whatever it might be. So a lot of transit ISPs or ASs are now going to IPv6 only. Yeah. And we'll talk about carrier grade NAT. This is also an issue. So a lot of ISPs want to move away from carrier grade NAT. I'm going to talk about that in a moment. Okay. Over 50% of internet content is available on IPv6. Basically, if you've got Facebook, if you are connecting IPv6 and you're going Facebook, Google, Netflix, LinkedIn, any of the major sites, Comcast, whoever it might be, you're going IPv6. Okay. And who's feeling the wave now? Well, we talked about ISPs. They're feeling it because they're running out of IPv4 addresses and they don't want to have to support both protocols in places where they don't have to. And also the mobile providers and the home market. So Comcast, for example, I believe at last count nationwide, they're well over 80% of their residences are now IPv6 enabled. And people don't even realize it. If you have a Comcast connection and a Comcast router that is, say, 2, 3, at least no more than maybe 3 years old, or you bought your own router, and which is not, you know, maybe a couple, just no more than a couple, 2, 3 years old, and chances are you're running IPv6 and you don't even know it. Most of the time, you're probably running IPv6 and you don't even know it. Okay, so home and corporate content is the next wave. Enterprises, they're kind of the slow one. We'll talk more about that a little later, but enterprises like the Cabrillo colleges and that sort of thing that don't really have to have an internet presence, meaning we have to have an internet presence, but it's not the, that's not the main focus of our market. We're not, I'll talk more about this a little later, but basically your experience connecting to Cabrillo's website is not going to determine whether or not you want to be a customer of Cabrillo, unlike a Netflix, a Facebook, a Google. Okay, Scenic. So as you can see here, Scenic is our ISP for the K-12 school system. Or say K-12, K-20 school system, from kindergarten all the way up through the UCs. Scenic is who allocates the IPv4 and IPv6 addresses to all the schools and colleges, etc. If you want, this is as of way back in 2014. This is how long they've been running out of IPv4 addresses. If you need more public IPv4 addresses, Scenic says they will allocate you a space no larger than a /27. That's only 32 public IPv4 addresses. And they'll only do that if you can show that you're going to be utilizing 85% of those now, and you're demonstrating that the additional space, you're going to need that additional space later. So they're severely impacted, which means the K-20 school system is also severely impacted. Okay, mobile. We look at the mobile providers. Yeah, people ask me, you know, I don't use IPv6. Do I, Rick? Do you have a mobile phone? Yes. Well, then a smartphone? Yes. Then you're using IPv6. T-Mobile is almost 100% IPv6. Matter of fact, T-Mobile devices are IPv6 only. They do this translation when they have to go to an IPv4 site called 464 XLAT. Verizon is well over 70%. This chart is showing as of late 2015, but they're well over 70% of their traffic is IPv6. So most of the time when you're on your smartphone, you're going IPv6. So Apple requires IPv6 support as of iOS 9 on all their apps. And pretty soon Apple has told its iOS developers that they're going IPv6 only cell service at some point. Facebook sees 20 to 40%, 1 or 2 seconds better performance with IPv6 because there's no NAT, carrier grade NAT, which I'll talk about. And that's a big issue for, you know, you may think, oh, it's 1 or 2 seconds. When you're on your smartphone, especially, you know, 1 or 2 seconds makes a difference. Facebook, LinkedIn, Microsoft, internally are IPv6 only. So it's here. It's here. If we look at the worldwide percentage of IPv6 internet traffic, or percentage of internet traffic going to Google, 25% of it as of early 2019 is IPv6. Now, what's interesting to note too is you're going to see that it took a while for it to get going. Okay. You know, so when you look at only, you know, 2015, only 5%, but you're seeing it go more and more. And actually the curve is going more like this. Okay. All right. This is an interesting, you can go here to 6Labs, Cisco, Comdat Stats, but here, just for the United States, for example, we can see IPv6 deployment over 50%. Transit ASs, so I talked about what a transit AS is. 67% of traffic going over a transit AS is IPv6. Over 50% of internet content is IPv6. So there's a lot more of it than people may realize. And also the interesting thing is that, you know, we really have no choice. You know, that curve, like I said, right, it's just increasing because why? IPv4 address availability is going way down. All right. Okay, enough of that. But, you know, basically it's futile, right? You know, there's a saying that, you know, there's different ways to kind of keep IPv4 addresses alive. People are buying IPv4 address space from companies that are going under or no longer need them, or reallocating things. But there's a saying, trying to keep IPv4 address space alive is like rearranging deck chairs on the Titanic. Okay, it's not going to help. You need to eventually go to have a plan to deploy IPv6. Okay, let's talk a little bit about IPv4 and then how we got to IPv6. So IPv4 has been around a long time. Developed, look, January 1980 was the first RFC. And then the current RFC is 1981. I mean, that's how old this protocol is. It uses 32-bit addresses represented in dotted decimal notation, provides for just under 4.3 billion addresses. Why not more addresses? Well, it seemed like a lot of addresses at the time, right? But let's take a look at the world in 1981. 1981, I was just a couple of years out of college. There was about 1-to-1 ratio with the world's population. What was the internet like in 1981? Well, most people had never even heard of the internet. There was no World Wide Web, no mobile devices. People didn't really care. Most people interacted with computers using mainframes and mini computers. The IBM PC was just introduced using MS-DOS, or PC-DOS it was called at the time, and was beginning to overtake the Apple II. And people weren't even thinking about networking these things. It was still mostly hobbyists that were buying these personal computers. And IP, just another protocol. There were other networking protocols out there, SNA, DECnet, etc. I'll talk a little bit more about that in a moment. So why transition to IPv6? By the way, before we get there, I want to mention something here, if I can find the quote that I've got. Let's see. Yeah, I want to mention something that Vint Cerf said. Says, so this IPv6, you all know that we are almost out of IPv4 address space. Vint Cerf, we'll talk about him more in a moment, is kind of considered one of the fathers of the internet. Played a large part in the ARPANET, and we'll talk more about him in a moment. But he says, so you all know that we're almost out of IPv4 address space. I'm a little embarrassed about that because I was the guy who decided that 32-bit was enough for the internet experiment. My only defense is that choice was made in 1977 when they were developing IPv4. And I thought it was an experiment. The problem is the experiment didn't end, so here we are. So Vint Cerf is one of the big proponents of going to IPv6. Okay, so why transition to IPv6? Mentioned in 1990s, so let's go to the 1990s. That's when the World Wide Web came about. Everyone was beginning to get on the internet. They had a reason, this new web thing, websites. Internet routing tables were growing rapidly. 20,000 routes in 1994. By the way, internet routes are now over, I believe, over 800,000 routes. The IETF, so we'll talk more about them, but they are the ones that develop the internet standards, the RFCs. They realized that we're soon going to run out of IPv4 address space and something had to be done. So short-term solutions. NAT. Okay, we'll talk more about NAT, network address translation, and its use of private address space. So these two things came out, were developed, and in combination, they have really saved IPv4 over the last, what are we talking now, 30 years? CIDR, classless interdomain routing. I'll talk more about that in a moment. So those are the three short-term solutions. The long-term solution was IPv6. Now, take a look at IPv6, right? December 1995. Yeah. Okay. I don't know if you saw it. It says my internet connection is unstable. Hopefully we're still good. All righty. So let's talk a little bit about going to classless. So I've talked about this in my CIS 81 class a little bit. We used to talk about this a lot more, but this is how IP addresses used to be allocated. You either got a /A address, /A, Class A, Class B, or Class C. Okay, and Class A address was a /8, /16, or /24. The problem was there's only about 126 of these Class A's. So 126 corporations, institutions, or whatever had 50% of the IPv4 addresses. This allowed for, /8 gave you 16 million host addresses. Wow, that's a lot, more than they needed. Everybody else, 16,000 people, could get an address of 65,000. So that was the Class B, probably still more than they needed. Everybody else got a Class C, a /24 of 254. So you had a huge amount here, very big amount here, and very few here. So it wasn't the best way to allocate IP addresses. I want to say the best. We look at it now, right, and say this, not the best way to allocate addresses, that you either got way more than you needed, or maybe not quite enough. But you got to remember what the internet was like then. People, probably a Class C was, even this was more than enough for most organizations at the time. All right. So what they did was they moved to classless interdomain. So they moved from where, instead of just getting one of these in red, a /8, /16, /24, you could get any number of prefix lengths, subnet masks, that gave you a variety, more of a range of host addresses. It was a better way to allocate the limited number of IPv4 addresses. Okay, and that's where we are today. Although you still hear people sometimes refer to as a Class A or Class B address, but that's pretty much obsolete. NAT. So NAT is really what has saved IPv4, along with private IPv4 address space. What NAT does is, internally, you can have a private IPv4 address. So a lot of people get the 192 at their home, 168, maybe a 1.0 network /24. Okay, millions, if not billions of people probably have this at home. But that gets translated to a single public IPv4 address here. Okay. This really just hides your network. It's not considered a security feature. IETF does not consider this security, because if this was security, that means all of us at home, all of us at work. By the way, this isn't just for home. This is almost every institution out there. Really every company, every school, business, home uses private address, IPv4 addresses, and NAT to connect to the internet. So if NAT was security, then we wouldn't have to worry about security, would we? Of course, we have to. So NAT is not security. And I'll point you to a little video that talks a little bit more about that if you're interested. Okay, let's continue here. So I've talked about carrier grade NAT, CGN, sometimes called as large scale NAT, or NAT 444. What this is because we have our private IPv4 address space at home or in our company, but because ISPs are running out, what they are doing is translating your private address to another private address, sometimes using this RFC 6598 space, which is this address, or could be also 1918 address space, same as we have here, like a 10.0 or 192 address. So they translate it from private to private, or your router translates it from private to private, and then before they send it out to another ISP, they translate it to a public address. So this is getting NATed twice. More latency, more delay, more issues that can occur. And NAT breaks the end-to-end principle of the internet, meaning that any device should be able to communicate to any other device directly. Okay, but NAT breaks that because we can't. You cannot at home ping your house, let's say, ping my house, because we both have private addresses. Okay, we can't video chat with each other directly without going through a third party like Skype. We both connect to their public address, and they allow us to talk to each other. All right. So here's a little example of NAT. Okay, so we can see the source IP address is a private 10 address. Your router connected to the ISP translates it to a public address. Okay, your source address is a public address. Notice the destination address is already a public address. So that's why we can connect to this public web server. Coming back, the destination address is your public address, but your router will translate it back to your private address. And it actually uses a form of NAT that we call port address translation that allows literally thousands of internal addresses to be translated to a single public address. Okay, what about IPv5? Okay, so before we get to IPv6, what happened to IPv5? Well, IPv5 was never a separate IP protocol. There was a protocol suite known as Internet Stream Protocol. It was experimental to help provide with quality of service over real-time multimedia applications. And the idea was when it was carried over IPv4, so it used IPv4, but it changed the version number to a 5. Although never deployed, there was an RFC on it, so that version number was taken. I'm going to talk a little bit here, and I'm going to try and go through this kind of fast. I've got it in my book if you're interested, but there's a great book called Protocol Politics. I want to talk a little bit about the politics of IPv4 and IPv6. I do this because I think it's very fascinating and maybe helpful to the students that you see that protocol development is a human activity as much as a scientific activity. That people's opinions and people's personalities and just, you know, it's, I'm lost for words here, but it's the people that get involved in this. And it's not necessarily all straightforward. Let's take a look. I'm going to try and go through this fairly quickly. I got a lot of slides on it, and let me go through it fairly quickly here for you. But 1990, the internet was very US-centric. That's because it was developed in the US. No Amazon, no Netscape. Americans were the predominant users, 73%. Let's see. So here's a world mapper shows what the internet users look like in 1990. And look at the US here in purple, right? You can see that it's very US-centric. Okay, so there's our buddy Vint Cerf. Okay, he was in charge of something called the IAB. At the time, it was known as the Internet Activities Board, later named the Internet Architecture Board. Okay, they had ultimate responsibility for the direction of the internet. They also managed the RFC process, oversee the IETF. Okay, I'm going to go through some of this very quickly here. Okay. The internet's core philosophy was working code through rough consensus, meaning make sure it works and make sure most, rough consensus. We for the most part, we agree on this. Okay. I'm going to go through these here. This is showing the IAB, but it was very US-centric. Okay, the IETF. So this is who makes the internet standards, writes the technical specifications, that are used even today. Okay, they were established in 1986. At the time, no formal membership, mostly Americans. And as 1990, they started talking about the shortage of IP addresses. Okay, and that they realized that by 1994, we were going to run out of IPv4 addresses. Okay, and the IAB, who oversaw them, were also concerned. Okay, so I mentioned the IAB, mostly Americans, IETF, mostly Americans. Okay, this is just, again, talking about how IP addresses were once allocated. There's kind of a history of that. John Postel was the guy that did it early on and then handed it over to a place called SRI. Then eventually, this is all back in the early days, so we don't need to go into this, but this is before the regional internet registries were created. But the IAB, they had some concerns. One of their big concerns is they wanted to be more, address assignment be more internationally distributed. Right now it was very US-centric. John Postel, SRI, which was in Marina del Rey, California, right near where I was going to college. USC was involved at one point of managing this. So you can see very US-centric. They wanted address assignment to be more international. They also wanted kind of the internet to be more kind of less US-centric and more global. So they thought, well, we start looking at having IP addresses allocated by international organizations, which started to bring up the whole idea of the regional internet registries. IANA would still remain in control, centralized control, but then they would hand it off to these, what was being developed at the time called regional internet registries. And everything was still classful. Okay, so here was the big battle that we don't really realize. There's a big battle between, there's this organization called ISO, International Organization for Standardization. They are not, that's not an acronym. That ISO itself is Greek for equal, meaning everybody is equal. But they had a protocol suite called OSI. Okay, it was not US-centric, not developed by IETF. It was developed by ISO. There was kind of their job early on to be developing a protocol suite. You can kind of see it over here. Let me use this. We have the TCPIP protocol suite going on, but we also had the ISO and their protocol suite called OSI happening. Okay. Also, AppleTalk had their own suite, Novell NetWare, but these were mostly for local area networks. But there were other ones. There was SNA, there was DECnet, there's Banyan Vines. So it wasn't for sure that TCP/IP was going to be the protocol suite of the internet. Matter of fact, ISO OSI was supposed to be the protocol suite of the internet. Okay, let's get through this here. Okay, so 1990, the US government mandated that all government products conform to the OSI standard. United States Department of Defense, proponent of TCP/IP, knew this was inevitable, and they were beginning to support more of the OSI vision. So here's ISO, by the way. If you're not familiar with ISO, who developed the OSI protocol suite, they're involved in all kinds of standardization all over the world for everything. You can see over here on the right, quality management, environmental management, country codes, all kinds of stuff. They have, I would say thousands, I'm sure, thousands of different standards that they deal with, from food to health to you name it. They're involved. Okay, so let's get through this. By 1990, it wasn't clear who was going to win out, TCP/IP or ISO. OSI was deployed very limited. They did have the backing of international governments, including the U.S. National Institute of Standards, and by some large networking companies, including DEC, Digital Equipment Corporations, which was a big competitor of IBM at the time. That's where Radia Perlman was working at the time, and she was a big proponent, and kind of still is, of OSI. TCP/IP, it was out there working. It was the dominant protocol suite, but it wasn't supposed to be the one that was going to be there forever. OSI was supposed to be the one that was going to be used. Okay, they had the backing of the technical community, IETF, because they're the ones that developed that. And they had well-documented RFCs. Okay, so anyway, IAB had to do some soul searching, and the steering group of the IETF had to figure out what was going to happen in 1991. Okay, they looked at several things, including, okay, let's take a look here. This is interesting, I think. Looking at which protocol to use. Should we have OSI and TCP/IP coexist indefinitely? Should TCP/IP be replaced by OSI? These were the different alternatives. Maybe OSI should fade away and TCP/IP remain the protocol suite of the internet. Or let's develop something completely different. Not TCP/IP and not OSI. Okay, this was a very, very spirited debate and very controversial. A lot of people had a lot of differing opinions. And a lot of it centered around OSI or TCP/IP. Almost everybody in the IETF community and US kind of, except for certain big companies and that, but the technical community was really backing a lot of TCP/IP. But it was kind of OSI or TCP/IP at the time. Okay, I'm going to get through this here. Okay, a couple of retreats happen. Let me just kind of, you can read through this if you're interested. My PowerPoints are out there, and it's also in the book. Let's see. Let's just kind of get through this here. So which one was going to win out? Okay. By the way, why IPv4? How did that come out? There was no official predecessor to IPv4. It branched off from the development of TCP. We had TCP version 1, TCP version 2, TCP version 3, which then separated. IP used to be kind of they used to think TCP used to combine both IP and TCP. And then they pulled them apart these were when all this was being developed, back when TCP v3 and IPv3. So then when it came formalized, we had TCP with IPv4. All right, anyway. IAB wanted more internationalization because there's mostly, IETF is mostly American. So Vint Cerf, who led the ISOC, he was the one of the Internet Society. He was kind of the main guy. Let me kind of get through this. Developed ISOC. He was kind of in charge of what was kind of the facilitator, let's say, of the internet at the time. They developed ISOC at this point to kind of be more of a managerial and legal entity of the internet. But let's move forward of this here. But he was trying to make it more international. So let me kind of get through this. I'm going to get to the heart of this here in a moment. Talked about IPv5. So what had happened? Oh, let me back up. Sorry. So in 1992, the IAB, without referring, let me kind of show you where I'm at here. The IAB, without discussing this further with the IETF, decided that they were going to replace IPv4 and what with OSI's network layer protocol called connectionless network protocol. So they were going to get rid of IP and use what was called CLNP, that which already existed, was part of the OSI protocol suite. Then they would run TCP and UDP on top of it. So that was what the internet was going to look like. And by the way, they're going to call it IPv7. Why? They erroneously kind of blew it and forgot that there wasn't an IPv6 yet. Okay. Anyway, let's see. There we go. Sorry about that. All right. Almost done with this. IETF was outraged. They're the ones, right? The whole TCPIP, you know, they were outraged. And they let Vint Cerf and ISOC know about it. They did not want ISO to have control, because ISO is kind of a very, not kind of, they are a very bureaucratic organization. ITF was very lean and mean. They got things done in a timely manner. ISO, very bureaucratic. Okay, so basically they revolted. They said, you know, no way. You can't just mandate that OSI's CLNP is going to replace IPv4. So because Vint Cerf and the others at the IAB heard about it, they got fried. They got the message. They said, and no fault of Vint Cerf and them. They were trying to make this a more international protocol suite and thought they could just mandate it. So they withdrew their proposal of using CLNP. So this is early 1990s. Okay. So what they did was, I'm just kind of going through this real quick. They did an RFC, IPNG, next generation. Basically 1993, they said, okay, let's do a call for white papers. Basically, who has proposals for the next version of IP? 4 actually came in. One of them was not even really looked at because it was way out there. That way, I wasn't doable. There were 3 that was left out there: catnip, SIP, and tuba. SIP was IP, which actually become IPv6. Tuba was the ISO standard, what they wanted, and catnip was kind of a combination of the two. I'll just let you know that what happened was they decided on for IPNG, what it was going to be was, I think I've got it here, the recommendation that they were going to use was SIP. We're almost done here. I think I've got this. I'm trying to just get through these slides here. So what was recommended was that they were going to use SIP, and they were going to use a 128-bit address space. Sorry, I kind of went through these a little fast here. Let's see. Here we go. So IETF would preserve control of the new standard. It would be named version 6, and it would be a 128-bit address. So that's kind of the human side of all this, which I know maybe it's a little boring for a lot of people, but I find is interesting because this, sometimes we look at these protocols where, well, this must be perfect because people knew exactly what they were doing. There's a lot of infighting and a lot of debate on what is the best way to do things. And remember, the internet is an evolution of technologies. It's what was available then and what they could do then, what was needed then, and then just kind of evolved into what we need done now with the technologies we have now. And you got to remember, we can't just throw out all the old stuff and develop something new. We have a lot of devices, billions of devices worldwide that have certain types of interfaces, running TCPIP now, running Ethernet. You can't just, and that's why, IPv6 there's not just an on-off switch. We're not just going to go to IPv6 like January 1st, 2021, because there's too many devices embedded with older protocols, older technologies. And we have to take that all into account. All right. So anyway, we're going to move forward on to the IPv6 primer will be the next lesson. And I hope you found this informative and learned a little bit from it. Okay, great. I'll see you in the next lesson.